Hey guys, welcome back. This is Coach Miller, and we're going to jump right into some problems dealing with the gas laws. Okay, we kind of laid some groundwork in the first video and talked about some key terms, but the first gas law that we're going to look at is the combined gas law, and it's called that for a reason. It is a combination of a couple of different gas laws, and we're going to actually look at all of those in just a minute. But anytime you're using the combined gas law, you have pressure, volume, temperature, and number of moles possibly changing. So you have more than just two variables changing. So we're going to look at how we would solve these problems. So here's an example. What would be the volume in liters of an 8.9 liter sample of gas at 100 degrees and 113 kilopascals if the conditions were changed to standard temperature and pressure? Now keep in mind, standard temperature and pressure is always the same. It's 1 atmosphere and 0 degrees Celsius. That's on the back of your formula chart. So it's not a value that you necessarily have to remember, but you do need to know where to find that. So the first thing I like to do is write down what I'm given in the problem. So the first thing I'm given is an initial pressure. My initial pressure is 113 kilopascals. Okay, my initial volume is also given to me. It's 8.9 liters. 8.90 liters. And the initial temperature I'm also given. You're told it's 100 degrees Celsius. But remember, we like to put that in Kelvin. So 100 degrees Celsius, we add 273 to that to get Kelvin. So it's actually 373 Kelvin. Okay, so what are we looking for? We are looking for volume. What would be the volume? So the volume that we're looking for is V2. That's my unknown. Okay, so that means I must be given a pressure, which I am. It's 101.3 kilopascals, and I know that because I'm told it's standard temperature and pressure. So look down here. I know that 1 atmosphere is equivalent to 101.3 kilopascals, so I can make that that translation there. And my final temperature would be 273 Kelvin, or 0 degrees Celsius. Okay, so the only value that I'm not given here is my V2, this one right here. Okay, they say nothing about moles, so I can take that out of the formula. Okay, if it's not mentioned, then we can assume that it remains constant. Okay, so now what we need to do is set up this formula to solve for V2. Now, anytime you have two equations set equal to each other, you can cross multiply. Okay, so if I cross multiply this, remember the ends are gone. If I cross multiply, I would be left with P1 V1 times T2 equals, cross multiply this way, P2 V2 and T1. Now, remember, V2 is the variable that I want to keep by itself. So in order to do that, I'm going to divide by P2 and T1 on this side so that they cancel out, right? And anything you do to one side, you must do to the other side of the equation. So P1 V1 over T2 divided by P2 and T1 equals my variable that I'm trying to solve for. So now I can just plug those variables in, or plug the values in. So I'd be given 113 kilopascals times 8.9 liters times 273 Kelvin. And I'm going to divide that by 101.3 kilopascals and 373. So if I multiply everything on the top, right here, and divide by everything that's on the bottom, the value that I'm given, or the value that I come up with, is 7.27 liters. That is my final volume. So what will be the volume in liters if the conditions were changed to standard temperature and pressure? It would be 7.27 liters. So in this problem, I had pressure changing, volume changing, and temperature changing. So I have to use the combined gas law. All of those variables are changing. You've got to use the combined gas law in order to find that value. Okay, now, what happens if something remains constant and you're told that it remains constant? Well, we can break that combined gas law down. Okay, notice the combined gas law was P1 V1 over T1 equals P2 V2 over T2. Well, if temperature remains constant, then I can simply take it out of the equation because I'd be dividing by the same value. So if the temperature was 100 degrees over here and it's 100 degrees over here, then there's no need to even have it in the equation because it remains constant. Okay, so keep that in mind as you're trying to decide which equation to use for each problem. So in this problem, you're told that you're told that temperature remains constant. You're given 1 liter of a gas at standard temperature and pressure, and it's compressed to 473 milliliters. What is the new pressure of the gas? Okay, first thing to keep in mind, pressure and volume are inversely related. That means as we increase pressure, we're going to decrease volume, and vice versa. Okay, so whatever change I make to pressure, it's going to be the opposite to the volume. Okay, so keep that in mind as we look through these problems. Again, start with what you're given in your problem. I always like to write down all my variables, okay, and write down what they are given to me in the example. I'm told that I have 1 liter of gas. So there's my initial volume, and I'm told that it's at standard temperature and pressure. Okay, if it's at standard temperature and pressure, then I know it's 1 atmosphere. If it's 1 atmosphere, then I can also assume that it's 760 millimeters of mercury. So we're going to use millimeters of mercury here, just because I think it'll be an easier value to deal with. And my final volume, you're told it's compressed to 473 milliliters. Now, my first volume is in liters, so I've got to convert that second volume to liters as well. Remember, there's 1,000 milliliters in 1 liter, so we're going to make that 0.473 liters, and we're looking for the final pressure. So P1 V1 equals P2 V2. That's the formula that I start with. I'm trying to solve for P2, so I got to divide by V2. V2 will cancel out, and anything I do to one side I must do to the other. So I'm left with P1 V1 over V2 equals P2. This is the final pressure. That's what I'm looking for. So now I can go back and just simply substitute those numbers for the variables. So what is my initial pressure? It's 760 millimeters of mercury. What is my initial volume? 1. And I'm going to divide that by 0.473. My final pressure is going to be 760 divided by 0.473, which will give me 1,607 millimeters of mercury. So volume went from 1 liter to 0.473 liters, so it went down. So we would expect pressure to go up, and it did. It went from 760 to 1,607. Moving right along. What happens if another one of those variables is held constant? Here you have Charles's law. Charles's law is when pressure remains constant, and the only thing changing is volume and temperature. Okay, volume and temperature are directly related. So in Charles's law, if temperature increases, then volume should increase. And if temperature decreases, then volume should decrease. And we'll see an example of this in just a minute, a real life example. Okay, so here's our problem, example calculation. A man heats a balloon in the oven. Now, why you would want to cook a balloon, I don't know, but let's work through this. Heats a balloon in the oven. If the balloon initially has a volume of 0.4 liters, so there's my initial volume, my starting volume, so there's V1, it's 0.4 liters. Okay, if it initially has a volume of 0.4 liters and a temperature of 20 degrees, so there's my T1, 20 degrees Celsius, or 293 Kelvin. Okay, remember, always use Kelvin in your values for temperature. That way we never have a negative value. What will the volume of the balloon be after it heats to a temperature of 250 degrees? So we're looking for the new volume, and we're given the final temperature. it increases to 250 degrees. 250 degrees plus 273 gives me 523 Kelvin. So pretty substantial change in temperature there. What would be the change in volume? Okay, as one goes up, the other should go up as well. So my volume should be higher than 0.4. Let's do the math here. Okay, we're trying to solve for V2. So again, we have two fractions set equal. I can cross multiply. So if I cross multiply, that'd be V1 times T2 equals V2 times T1. I'm trying to get V2 by itself, so I'm going to divide by T1. Those will cancel out. And anything I do to the one side over here, I'm going to do to this side over here. So my final formula that I'm actually going to use is V1 times T2 divided by initial temperature equals my final volume. Okay? Now I go in and substitute those numbers for the variables. So what is my initial volume? It's 0.4. My final temperature is 523. And I'm going to divide that by my initial temperature, which is 293. Multiplying the top and dividing by 293, my final volume is 0.7 liters. So still not a whole lot, but 0.7 is definitely greater than 0.4 over here. So we did have an increase in volume with an increase in temperature.
This is heavy duty, Doc. This is great. Does it run like on regular unleaded gasoline?
Unfortunately, no. It requires something with a little more kick. Plutonium.
Plutonium. Wait a minute. Are you telling me that this sucker is nuclear?